Or state space solutions and the realization. Okay, so let's begin with introduction. So let me draw a table. So basically we are considering linear system. And in the linear system, there is lumped system and there is distributed system. And in the lumped system, there is linear time invariant lumped system and linear time variant lumped system. And also in the distributed system, linear time invariant, linear time variant. So, given this kind of linear system, we want to get solution. Final goal is to find specific solution according to time or according to x. So basically, in whatever case, lumped or distributed, time variant or time invariant, we can find yt equal to integral t equal to from initial to some specific time g t tau u tau d tau. Basically, we can get the solution in this way. So g is impulse response. But as you can see, this is not easy to calculate. It's complex to calculate. So this is general, but in practice it's very difficult to calculate. So let's say this is original case, original solution. So another way is to discretize it, to make it in discrete form. So discretization. Discretization is basically some kind of approximation, approximating this solution. Then, we discretize it for every delta, and time is substituted by k delta, k for integer. So, integral goes to sum. So from k nothing to specific k, g k delta, m delta, u m delta, multiplying delta. So we might be able to discretize it and calculate it. But the problem is that it's inaccurate because it's kind of approximation. This is inaccurate. Then we might be able to think about transfer function, Laplace transform. If we have GS, if we have US, then we can simply get YS. So, given the Laplace transform YS is GS Laplace transform, US Laplace transform. Then, if it's lumped system, then the Laplace transform is rational. So this is rational. But in here, if it's distributed system, then here GS is not rational anymore. This is irrational. For example, in here there are kinds of E terms like this, irrational. So it's not easy to get the inverse Laplace transformation. But if it's lumped system, in other words, if you can specify a few variables that fully describe the system, if you pinpoint a few specific properties that specify the system, then the transfer function becomes rational. So this is rational in lumped case. So if this is also rational, in other words, if the signal is just normal signal, let's say, that we can see in everywhere. Commonly, we can observe this kind of signal. So if those two functions are rational, then we can do the inverse Laplace transformation. And we can find YT. Okay, then we got the solution. This is accurate. It's not inaccurate, not like this. It's not an approximation. Everything fine. Except that this procedure is very sensitive to noise when there are multiple poles. You have learned the control theory in your undergraduate course. There's some pole. So if there are multiple poles, it could be very sensitive in some specific cases. So it's not recommended for multiple roots. It's not recommended. Then, what's the recommended way of finding solution? It's state form. So we define some state in lumped system. Of course, in distributed system, we cannot define states because they're infinite states. So we cannot be able to solve it through state space form. But if it's a lumped system, we define the states. In continuous case, time variant or time invariant, let me write it in general form. Okay, if we are able to write down the state space form, then this is simply first order differential equation. First order differential equation. We can solve the first order differential equation. It may be exponential something, right? It should be exponential something. Then, if we can find this from the differential equation, then you can find YT. In other words, we can find solution for every t. So, writing down a transfer function. Transfer function exists for any cases. Writing down transfer function in terms of state space form, we say realization. And there are, transfer function is unique. There is only one transfer function. Given the system, transfer function is unique. But its realization could be multiple cases. Because if A matrix can be substituted by its similar matrix, then state space representation can be different. because this is representing internal state. In representing internal state, you can put emphasis in, you can represent the internal space using different bases. So this could be, there could be multiple cases, and this is unique. So we will find a solution in the state space form. First, we will find solution from this differential equation, and then we will find yt. So, chapter 4 is organized in time invariant first, and time variant. So let me write down chapter organization. So, linear, nonlinear, lumped, distributed, time invariant, time variant, and continuous, discrete. There are four different aspects: linear, nonlinear, lumped, distributed, time invariant, time variant, continuous, discrete. So let me write them down for lumped case, linear lumped case, for continuous and discrete cases. So linear lumped. So linear lumped, and in the textbook, LTI first and LTV later. So basically this part. And we put continuous here, discrete here, continuous here, discrete here. Continuous here, discrete here, continuous here, discrete here. So first we will see solution. Solution of state space 4 on chapter 4.2 in continuous case, and 4.2.1 to 4.2.2, we will see that for discrete cases. Then, I told you that there is multiple representation for this state space representation. So, there are equivalent representation. Regarding the equivalent representation, we will see at 4.3 chapter. And given the transfer function, we have a few methods that can make them in space form. That's what we say realization. And we will see that for 4.4 for continuous case. And then we go to time variant case. So in 4.5 we see the continuous solution for time variant case, and 4.5.1 we see that for discrete case, and 4.6 and 4.7. So coverage of midterm is chapter 1, 2, 3 plus this part. Solution part for linear time invariant case. That's coverage of midterm that we will have next week, right on here. Closed book. I put emphasis on understanding. I mean, you don't need to memorize all the equations, all the procedures. That's unnecessary. But I want you to understand the procedure. I want you to be able to solve some problems. I want you to understand some concepts. So you don't need to memorize. If you think it's too it's too much to memorize all these things, then don't memorize it. If it is necessary, I will put it down in the problem. I'll write it down if it's needed. But you need to follow up the procedure, how it's being derived. You need to understand the concept, something like that. So today we will cover up to this point, and we will do a very brief simulation regarding those things. And then next week we're going to have midterm. Questions up to this point. How can you get the transfer function for GS? It's easy because we give impulse response. We give impulse to the system and observing the output. Then if it's linear system, then we may have this kind of specific GT tau. Given that GT tau, do the Laplace transformation and we can get this kind of thing. And if it's lumped system, we can change it, realize it in the state space form. Otherwise, we cannot do that. So this is overview of chapter 4. And let's keep going to find the solution. First part, solution of LTI, linear time invariant, continuous lumped system. So given the state space form, let's assume that the state space form is given. Then it's simply solving first order differential equation. Solution of linear time invariant lumped. Of course lumped, because if we have state space form, it's lumped. State equation. So we may write in continuous case time invariant. So we don't need this t because the system is time invariant. So this is constant matrix A and xt plus but yt is c xt plus dut. This is general form of state space representation. So my major is robotics. So if I say this is x coordinate, y coordinate, and if it's phi, if it's x robot, and if it's y robot, then robot's center point state can be described by xr, yr, phi r. And here, control input goes to motor. There's one motor here, the other motor here. So some U control input, we control the motor. So U right and U left is control input. This is control input, for example. And if you have GPS, then GPS, let's say it's output. Output is if you're interested in just point, not orientation, then you might be able to write it in this way. So this is C matrix. So given the state, it's just yielding output on your interest. Now XY is coming as a result, and this is control input, and we might be able to build some kinematic relationship between this input and state. Of course, in the beginning, it's nonlinear equation. In the beginning, it's nonlinear equation. But you know, you can linearize it, right? Linearize it, and you can discretize it. So finally, you can make some kind of linear and discrete state space form, which is good for your programming. If it's continuous, it's not easy to do the programming. Okay, so in general, there is no U in the output. And B indicates how control input is exerted to the system. So in this case, if you give two inputs, it will somehow affect the system. That's B matrix. A matrix is how state is changed. So state transition matrix, how state is changed. And C is linking between state and your output. So each matrix A, B, C, D has its specific meaning. So its dimension could be very different. It doesn't need to be the same. For example, this could be n by 1. Then this is n by 1. This is m by 1. If we say the output is q by 1, then C is q by n. And if you say U is n by p, oh, it's not n by p, p by 1. So input, state, output has different. This is n vector, p vector, q vector. Then those matrix linking them. So this is n by n, this is n by p, this is p by 1, this is q by p. So in this way, they are synchronized in its dimension. So to find the solution, let's prove a lemma that d dt exponential matrix t equal to a exponential at or e at a. Let's simply prove it. Proof is straightforward by using Taylor expansion. So EAT is basically identity plus TA plus T square 2 factorial A square plus T cubic 3 factorial A cubic plus, and goes on. This Taylor expansion. And if I do the differentiation on here, if we do the differentiate this, d dt exponential at is, this is simply from k equal to 0 to infinity, 1 by k factorial tk ak. So term by term differentiation gives k begins from 1, k 1 to infinity, k minus 1 factorial 1, tk minus 1 ak. Then it's easy to show that this is simply a in the front, something, and something a, that this goes into here. Therefore, differentiation of EAT is A EAT equal to EAT A. So we proved this lemma briefly. For matrix case, A is matrix. Then let's get the solution, one in time domain and the other one in frequency domain. Time domain solution. So the first, we get xt from here. We get xt, then we get yt from the given xt. So the first step is finding xt from this differential equation. And let me write down, let me multiply e minus at on both sides for this differential equation. Then e minus at x dot t equal to e minus at a xt plus b e minus at ut. Then put it in this side. X dot t minus e minus at a xt equal to b e minus at ut. Then this is equal to d dt e minus at xt, because the first term is differentiation for this and the latter term is differentiation for this, is equal to then evaluating from 0 to t. Integral 0 to t for the integral, let's write tau inside variable because this is t, u tau d tau. Then the first term is e minus at xt minus e nothing minus x nothing equal to integral 0 to t b e minus a tau u tau d tau. Therefore, finally xt is multiplying e at, then e at x nothing initial condition plus 0t, e at goes to inside this matrix, b e minus a t minus tau e at e at, okay, t minus tau, it should be plus, and minus a tau, right, e at, okay, u tau d tau. Okay, this is xt. So the procedure, you should understand the procedure, but you don't need to memorize this kind of equation. Okay, no need to memorize this kind of equation. If it is necessary, I will give some hint, or I will write it down in the problem. Then let's verify whether this equation is right or not. Verification. For the verification, we check the initial condition. First, check the initial condition, whether this satisfies the initial condition. And second, we verify whether its intermediate state is correct or not. For the initial condition, let's see whether x, if I put t to 0, then x0 appears or not. I will put x, instead of t, I will put 0. Then e0, x0 plus 0, 0. So this is the same to initial condition. So the solution satisfies the initial condition. And to check the intermediate condition, we need adopt one equation. Let's adopt one equation that partial differentiation of t0t ft tau d tau equal to t0t partial differential equation f t tau d tau plus f t tau equal t. Let's adopt this equation. Now let's differentiate the solution. Let us differentiate the solution, and then let's see whether the original state space form is recovered from here. So I will differentiate this equation, xt, equation alpha. Then the first term is x dot t equal to EAT differentiation is A EAT x nothing plus, if I differentiate this thing with respect to t, then it's the same to do the differentiation for this function. There's some function t and tau function inside, and we do the differentiation with respect to one variable t. So we might be able to apply this representation. So from t nothing to 0 to t, we do the differentiation with respect to t. If I do differentiation with respect to t, then a comes front. Then b a e a t minus tau. So a comes to front. A here, E, A, T minus tau, and remaining terms, plus this thing. This is E, A, T minus tau. If I put tau, T instead of tau, here I put t to tau. Then this is 1 and it becomes ut. So in terms of A, we have EAT x nothing plus integral of 0 to t E A t minus tau b u tau d tau plus, if I put t here, this is b u t. Again, this becomes xt our solution. Therefore, we have AXT plus BUT. So given the solution, we derive the original state space form that x dot equal to AXT plus BUT. This is real-time solution. And then we find the state space, we find frequency domain in Laplace transform. So time domain done, in the frequency domain. Seems like that once I wrote down that m multiplication n, when we calculate this, we take log and log m plus log n log mn. This is log m plus log n. From that, we can find the final output. Similarly, if there's time domain problem, real time domain problem, let's say differential equation, x dot is something something. If we take a Laplace transformation, then it's x ss, and here the calculation is simple, and we do the inverse Laplace transformation. In this way, we can solve differential equation. So this is transformation, inverse transformation. Similarly, this is transformation, and this is inverse transformation. And nowadays, I feel like that this is very useful, because here, if something, two factors are coupled. For example, rotation and translation, it's up to your major. What's your research field is different, but two different factors can be combined. They exist in multiplied form. Then it's not easy to analyze individual effect because they are coupled. They are affecting each other. In this case, for example, then effect of m, effect of n, it's not easy to divide. But if you take a logarithm, then effect of m and effect of n is divided. Then you might do the optimization here, minimize something or maximize something. Then you may do the inverse transform. By doing that, you can separately consider two coupled factors. So transformation enables those kind of things. Initially, if you want to minimize something like this, then it's not easy, right? Because they are affecting each other. However, if we take logarithm, then their effects are divided. So minimizing this is the same to minimizing this. In this domain, you can minimize each of them and just sum them. So separately thinking them, then get the final solution. So basically, transformation makes the problem more tractable. Transformation makes difficult problems more tractable. So in the same vine, differential equation, it's not easy to get the solution directly. But if we take the Laplace transformation, it's just table, right? Given the table, we take the Laplace transformation. And here, it's algebraic equation, plus minus multiple division. Calculate it. Then, according to table, we do the inverse Laplace transformation. Then we get the solution. So, time domain solution is given like this, based on differential equation. But frequency domain solution can be given as why this we say frequency domain, because S is complex number, complex variable, right? S is alpha plus j beta. This is complex number. This time domain. If it's complex number, then exponential s indicates exponential alpha plus j beta, which is exponential alpha, exponential beta plus cosine beta, exponential j beta, which is exponential alpha, cosine beta t, let's say t. Cosine beta t plus j sine beta t. So this is basically some kind of oscillation with specific frequency beta oscillation, and this is scaling factor. So if alpha is negative, it's scaling, decreasing, it's converging to 0. If alpha is positive, it's diverging to infinity. So if alpha, this is basically oscillation. Here multiplied the scaling factor. Let's say if alpha is negative, those two things are multiplied, then makes the final something. So here, this beta has something to do with the frequency, right? This is frequency part. So if it's say complex number, then we are handling something in the frequency domain. Again, here this and this is coupled. Red and black is coupled. If you want to analyze it individually, you may take logarithm. Then you might be able to handle their effect separately. And taking the logarithm back, that's the useful trick to utilize the transformation. Okay, anyway, we can do the frequency domain. We can get the frequency domain solution. And as we did that in the chapter 2, let me write down the result only. Laplace transformation of x's, simply that one. It doesn't need any verification, it's straightforward, right? Given the differential equation, it's very straightforward. S is coming with dot, and initial condition follows. This is very straightforward. So we have y, output is multiplying c inside the x hat. Okay, this is frequency solution. With this equation in hand, we do the inverse Laplace transformation to get the final solution. So when we're doing that, in the time domain solution, what's difficult is to find the exponential at. It's not easy to find exponential at. In frequency domain solution, it's not easy to find SI minus A inverse. Those things are not easy to find. Then, to calculate it, we might be able to utilize some minimal polynomial, that a function that satisfies this relationship and a function that satisfies this relationship. By utilizing minimal polynomial, we can find the value for fa. If we can find minimal polynomial for this, then we can find fa, and we can find fa in both cases. So let's do that through the example. So minimal polynomial, that's what we did in the last lecture. By finding the minimal polynomial, we can find the solution, xt. Given xt, we can find yt easily. Next example is find zero input response for x dot equal to okay. So given this differential equation, the solution is E at x initial condition plus 0t E a t minus tau b u tau d tau. Here, zero input response, so it's zero input. So this is 0 because there's no input. So if you're able to calculate EAT, then solution is straightforward. Now let's define, to calculate EAT, let's define F lambda, E lambda T. And let's calculate the eigenvalue for this. The eigenvalue for matrix A is lambda 1 equal to lambda 2 equal to minus 1. So in multiple roots, minimum polynomial is lambda plus 1 squared. So n is 2. Given n is 2, we can set the minimum polynomial as first degree. Because this is second order, we can set minimum polynomial in the first order. In this way. For n dot bar, which is equal to n equal to 2. Therefore, by Cayley-Hamilton theorem, if we put A and F, if we put minus 1, it should be equal to H minus 1. Because it's 2, we can do the one-time differentiation. So F prime minus 1 equal to H prime minus 1. There are two conditions should be satisfied. F minus 1, if I put minus 1 here, E minus T equal to, if I put minus 1 here, beta 0 minus beta 1. We have one equation. And here I do the differentiation. But this differentiation is with respect to lambda. So with respect to lambda, T E lambda T. T E lambda T. This is differentiation. And in the lambda, we put minus 1. So T E minus T equal to, differentiation with the lambda is beta 1. Beta 1. So we have minimum polynomial that beta 1 is T E minus T, and beta nothing is E minus T plus beta 1. T E minus T. So our minimum polynomial is, H lambda is beta 0 plus beta 1 lambda. Here, beta 0 and beta 1 is known. So if you want to find our final aim, FA, this is our final aim, FA. If you want to know FA, then put A instead of lambda in here. Then our FA is equal to HA, which is beta nothing identity plus beta 1A. Calculation is straightforward. Then we have E minus T plus T E minus T minus T E minus T Te minus T, E minus T, minus Te minus T. This is one example for time domain case. And by the same manner, we can calculate that then for frequency domain. Okay, for the given same matrix, we want to find Si minus A inverse. Then the characteristic polynomial should be the same, lambda plus 1 square. So n equal to n bar equal to 2. So we put function in the same way, S minus lambda inverse. And we put h lambda as in the first order, this minus 1. So beta 0 plus beta 1 lambda. And given lambda minus 1, we have f minus 1 should be equal to h minus 1. And f prime minus 1 should equal to h prime minus 1. Here, if I put minus 1, S minus 1 inverse is H minus 1 is beta 0 minus beta 1. And here, F prime minus 1 is either differentiation for this with respect to lambda. So this is let's do the differentiation for this. Let's do this step by step. In this case, trivial trick is to do the multiplying. Then, if I say this alpha, this is 1 rho alpha over 1. And the remaining part is this and this, which is simply differentiating with lambda is minus 1. So this is minus alpha square times minus 1. So plus alpha square over 1. So, okay. It's differentiation. I did the differentiation just for the first part. Then if I put lambda minus 1 and s plus 1 squared, s plus 1 squared equal to differentiation with the lambda is beta 1. Beta 1 is simply 1 by s plus 1 squared. So we have beta 1 and we have beta nothing from here. So given the beta 1, beta nothing, HA can be simply calculated. HA is simply HA, which is FA, which is SI minus A inverse. FA, which is SI minus A inverse, can be calculated by HA, where beta 0 plus beta 1 A. And beta 0, beta 1 is known from those two relationships. So if we calculate them, we have this kind of matrix. This is SI minus A that we want to find in the frequency domain. Then, given this, we can do the inverse Laplace transformation from table. That should be the same to EAT. And do the inverse Laplace transformation from the table. The solution is given to be like this, which is the same to the time domain equation. Okay. This is about chapter 4.2, finding the solution for state given the state space form. Can you give some questions? Please try it in hands, step by step, so that given problem, you might be able to solve it. Then, having 10-minute break, we'll start the next part. So we calculated EHAT using minimal polynomial, but it doesn't need to be always like that, because for given matrix A, for arbitrary the square matrix, we can decompose it using Q Jordan block, Q inverse, right? Then EAT can be Taylor expanded in Taylor series, Q J Q inverse plus 2 factorial Q J square Q inverse plus blah blah blah. That will make finally Q, how it will be? Q I plus J square plus blah 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 Q inverse, which is Q exponential JT Q inverse. So if we are able to calculate exponential Jordan T, then A can be calculated from in this way too. Then how exponential Jordan form T can be calculated? For example, if some Jordan form is given like okay, if this kind of Jordan form is given, this indicates that there are three Jordan blocks, and there are two different eigenvalues. This is multiplicity 4, but there were just two distinct eigenvectors. One eigenvector here, the other eigenvector here, for multiplicity, and there's one distinct eigenvalue and eigenvector. If we calculate its exponential, then for this part and for this part is straightforward. We just put exponential here, that's it. So it's separate term. But how the center part, the larger 3 by 3 part will appear, that's a different problem. Then let's calculate it. Let's calculate how it will be turned out to be. So that's connected to example 3.10. A Jordan block is given one Jordan block one Jordan block. So for multiplicity, lambda 1 is repeated by 4 times, but there's just one distinctive eigenvector. So this Jordan block is consistent. So you want to calculate FA, which is exponential A hat t. To do that, we set the minimum polynomial as h lambda. Because there's 4 multiplicity, the polynomial could go to up to degree of 3, 4 minus 1. It could be a minimum polynomial. But if we set this kind of minimum polynomial, the calculation becomes complex, so we put slightly different, still the third order, but slightly different characteristic polynomial in this way. Because lambda 1 is constant, there's no difference. It's still third order polynomial. Of course, beta 0 values may be different, but it's just different representation, basically the same. The inherent characteristic is the same, third order differential equation. So we have 4 conditions. Given 4 unknowns, we have 4 conditions. One is f lambda 1 should be equal to h lambda 1. So if I put lambda 1 here, then nothing, beta 0. Beta 0 is equal to f lambda 1. F lambda is e lambda t. So beta 0 is e lambda 1 t. We got the beta 0. The second condition is f prime lambda 1 is h prime lambda 1. F prime lambda 1, if I do the differentiation with respect to lambda, then t goes to front. So t e lambda 1 t equal to h prime lambda 1. If I do the differentiation, this disappears. Then beta 1, just beta 1 appears, right? Those things, if I put lambda 1 nothing, this appears, just beta 1 appears. So beta 1 is T E lambda 1 T. And third condition is F double prime lambda 1 is H double prime lambda 1. Similarly, if I do that, one more differentiation give T square E lambda 1 T equal to, if I do the double differentiation, beta 2 just appears. Oh, not only beta 2, 2 beta 2. Yeah, 2 beta 2. So beta 2 is calculated. Finally, triple prime. Then we have T cubic by 3 factorial E lambda 1 T equal to beta 3. So we have beta 1, beta nothing, beta 1, beta 2, beta 3 in this way. So given those beta values, we can calculate FA Jordan block, E Jordan block T, which is beta nothing plus, which is HA, is beta nothing plus beta 1, matrix A minus lambda identity plus beta 2, matrix A minus lambda identity square plus known beta 3, matrix A minus lambda I cubic, lambda 1, lambda 1, lambda 1, lambda 1. Okay. Then, simple algebraic calculation gives E lambda 1 T in the diagonal and T E lambda 1 T and T square 2 factorial E lambda 1 T and T cubic 3 factorial E lambda 1 T. This is exponential Jordan form. So if we are able to calculate the Jordan form, then we are able to find the exponential in this way. Okay, this is for continuous case. Now we will go to discrete case. Before going to the jump to the discrete case, any questions? Okay, so with the continuous case, we cannot do the simulation or we cannot do the calculation. So we need to discretize it. We have to make it in discrete form. Discretization. there's a naive way and a few better ways. If one say discretize this equation, one naive way, what will you do what will you try in the first place? You may try that the definition that x dot t is limit as t goes to the nothing is x t plus t minus xt divided by t. This is definition of x dot t. So a naive approach might be put this into here, then xt plus t minus xt is multiplying t here, at xt plus bt ut. And another naive approach is to express t as a discrete form. So let's say kt, k times t. So kth index. Then this is k plus 1t. So x k plus 1t equal to at minus identity. At plus identity. So t is scalar, so let's put in front ta plus identity x kt plus b t in the front because scalar t b ut. This could be one example of naive discretization. Oh, not t but kt. This is an example of naive discretization. But if you do like this, you will see that this is not a good solution. It seems like work, but if the problem becomes complex, then this solution may evoke lots of errors. So it will finally make a catastrophic disaster in your system. So it will fail finally. So we need some kind of better approach. In this time, I remind one of my friends. He said that low pass filter is not necessary. This is my friend. My friend said low pass filter in signal system. In signal system, there's multiple complex low pass filter, right? In complex form. Finite, infinite, response filter, blah, blah, blah. And he said those things are unnecessary. And he said that EKF is unnecessary, extended common filter. They are just complex, useless. And he said that all the things can be simplified. So he suggested a low-pass filter. For example, he suggests that AK, XK do like this. So if this is a control input, then current state is updated 90% from the previous state and just update input just 10%. Then it was slowly changing. Then it's some kind of low-pass filter. He suggests this and it really worked. So at that time I said, hey, you're genius. But as the problem becomes complex, this made some serious problem because this is too naive. Of course, this is a very special case of low-pass filter. So it's not good try like this. Also, he said that EKF is useless. And he said that his own filter doing similar work with like EKF. And it seems to be work in simple case, but finally it failed. So it's fast solution, but it's not good solution. So as an educated engineer, we need to take a better approach, a good solution. So this is naive approach. It will work for simple problem, but it's not going to be very effective. So what's the better way then? Better way is there could be various ways. For example, the first step, the first better approach is zeroth order holder. What's zeroth order? It's just it's constant value. So given a specific time, you assume that given a specific interval, the value is the same. And given the specific interval, the value is the same for some specific period. The zeroth order holder, ZOH. This is one approach. And what will be better approach? There could be various enhancement. One thing you can think about is why using this value, also use this value and connect them as a triangle. This is trapezoidal. This seems to be an advanced method, right? Then one may say that, hey, why you're using yt? Why not using y dot t? You may use not only the value, but also it's changing, the rate of change, right? It's tangential value. Then it's extended to the Runge-Kutta. Not only using the value, but also it's differentiated. Its rate of changes, then it's extended to the Runge-Kutta. And MATLAB is basically based on Runge-Kutta fourth order. There are Runge-Kutta second order, fourth order, blah, blah. And neural MATLAB simulations based on Runge-Kutta fourth order. So there could be, from the naive approach, there could be better approach. But in the textbook, the zeroth order holder case is described. So we will change this kind of continuous differential equation using the zeroth order holder. We will make it in discrete form. So the final equation will be xk plus 1 is a discrete form xk plus b discrete form uk and yk plus 1 yk is c discrete form xk plus d discrete form uk. So we'll find a discrete version of the continuous case. Okay, so by the assumption of zeroth order holder, ut can be assumed to be ukt, which we write uk for very specific time being, for very short time interval, from kt to k plus 1t. A very specific one-time step interval we might be able to assume in that scenario. Then the original solution of differential equation can be described by this is original differential equation. And if we increase k to k plus 1, k goes 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 to k plus 1, this way. Now, let's extract one EAT in front. We want to extract 1 EAT. Then this is EAKT x nothing plus the second integral. The integral is divided by 2. One from 0 to kt, the other from kt to k plus 1t. From 0 to kt, we extract E80 in the front, so this is EAKT, AK, kt minus tau, b u tau d tau, and the remaining is E A k plus 1 t minus tau b u tau d tau. Okay. Now the bracket, inside bracket, red bracket is basically x. This is xk. Inside bracket is xk. And thinking about the remaining part here, let's put this as alpha, for example. Let's put alpha as k plus 1 t minus tau. Then, if tau is kt, then d alpha is minus d tau. D alpha is minus d tau. And if tau is kt, then alpha is t, right? If tau is kt, then alpha is t. If tau is k plus 1t, alpha is nothing. 뭔가 다른 것 같은데? Just 1 second. Let me check it. KT and the original integral should be rewritten as for kt is t, k plus 1t nothing, e a alpha. And here, for this one step, one period, this is constant, right? This is simple constant. So u kt, it can go out of the integral. So u b is constant, u kt is constant. So it can go out of integral. And d alpha is minus dt minus d tau. D alpha. And I change the order by put 1 minus, and it's 0 to t exponential a alpha d alpha. So I may rewrite it as this form. Now let's think about it. Exponential a alpha d alpha. If I'm thinking about it, exponential integral from 0 to t exponential a alpha d alpha. Then it's straightforward because we can do the tail expansion. Exponential a alpha identity plus a alpha plus a square alpha square 2 factorial blah 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 blah. And we integrate it with respect to alpha. Then alpha terms will appear one more time. Then finally, in the alpha term, if we put t, it's it plus a by 2 t square plus a square 3 factorial 2 cubic plus blah blah blah. And we put a inverse in the front. Then here a remains, at remains. That makes t, so at. Here a square, t square. Here a cubic, t cubic. Everything okay, blah blah blah. It goes to like this. Except one thing, we don't have identity. We have, here should be identity. So we plus identity and minus identity. Then this part makes another one tail expansion. So this is A inverse exponential AT minus identity. Okay, this is how the red part is being changed. Then summing up, xk plus 1 is exponential at xk plus A inverse EAT minus identity times BUK. So we say this as AD, this as BD. So we have discretized version of continuous differential equation given the zeroth order order assumption. And this should be C. Discrete case CD, DD is the same. CD, DD is the same. So YK is CD, which is the same to C, and DD is the same to continuous D. So we discretize it using the zeroth order order. And now it's time to calculate. The solution for given differential equation. So we will find solution for this kind of given differential equation. The solution is very straightforward. Because if it's discrete case, solution can be inferred by repeating it as we increase the time step. You don't need to solve it. You can just increase the step by step. So x1 is ax nothing plus bu nothing. x2 is ax1 plus bu1. Then if we put x1 here, then it's a square x nothing plus ab u nothing plus bu1. Now you maybe already noticed that any number 3, 4, 5, 6, 7, 8, whatever number, it can be described by the initial condition and by all the control input up to that point. So it can be generalized in that way. So xk is simply combination of initial condition plus all the control input up to that point. All the control input up to the point. And what put in the here is this. So this is the solution of discrete time differential equation. And given this, you can easily calculate yk. Yk is just multiplication of cxk and dk. cd, dd, uk. So yk is straightforward from given xk. So in discrete case, the key is calculating AK, right? Similar to EAT, in the continuous case, AK also in the continuous case, we calculated this in this form. Similarly, in discrete case, we calculate this as like this. And the way calculating JK is same to the way calculating EJT. So if you have a J4, in this way, then exponential jkth power here there are two eigenvalues, and one eigenvalue has one distinctive eigenvector, but the other eigenvalue have two distinctive eigenvectors. So, as is diagonal, for this, it's straightforward, lambda 1k. For this, lambda 2k is straightforward. But for this, 3 by 3 Jordan block, we need to calculate it using h lambda, using minimal polynomial. You should be able to calculate that. Okay, so this is discrete case. And for the discrete case, we got solution. And we saw how to calculate AK from the Jordan form. Try it. You should be able to calculate it. Go home and try. So, questions up to this point? Just for a second.